Hello everyone. In this video, I will explain another example of first form. In the first form, we are using partial fraction expansion for impedance function. This is our impedance function. For this example, ZLC is equal to 12s to the power 4 plus 9s squared plus 1 over 6s to the power 3 plus 2s. It is a LC function. Then we have to construct the circuit diagram for following this LC impedance function. As for the first step, we have to check whether this function is realizable or not. There are several properties. General properties for RLC function and additional properties for LC networks. We have to check whether those conditions are satisfied. Before that, I will find the roots of the numerator and denominator to find zeros and poles. If we consider the roots of numerator, we can get roots like this is equal plus or minus square root of minus 9 so minus root 33 over 24. These are the two roots. I will consider first root plus or minus 9 minus root 33 over 24. From that, we can get plus or minus 0.78 J. And from the plus square root 33, we can get S is equal plus or minus 9 plus square root of 33 over 24. We can get plus or minus 0.37 J. There are four roots. It means four zeros from the numerator. And we consider the denominator. We can rewrite 2s 3s squared plus 1. Roots are s is equal to 0 and s is equal to plus or minus j over square root 3. These are poles. And if I draw zeros and poles in the complex S plane, this is imaginary axis, this is real axis. There are three poles at the origin and j over square root of 3, it is equal to plus or minus 0.58 J around this place, 0.58 minus 0.58. And there are four zeros at the 0.37 and 0.78, 0.78 minus 0.78. These are the representation of poles and zeros in the complex S plane. Now we will move to the properties of RLC network. In the first property, it says must be a rational function in S with real coefficient. You can see it is a rational function of S with the real coefficient. Then first one is satisfied. Second one may not have poles or zeros in the right half S plane. You can see this is the right half plane. There are no any poles or zeros in this plane. All are in imaginary axis. Then second one also satisfied. And the third property is may not have multiple poles or zeros on the j omega axis. There are no any multiple poles or zeros. Then third one also satisfied. And the fourth one is may not have the degree of the numerator and denominator differing more than 1. Numerator degrees, maximum degree is 4, this one. And for the denominator, maximum degree is 3. 4 minus 3 is equal to 1. Then it is not more than 1. Then fourth condition is satisfied. And fifth one is must have a non-negative real part for all s equal j omega. For that one, we have to calculate ZLC. If s is equal j omega, we can write 12 j omega to the power 4, 9 j omega square plus 1 over 6 j omega cube plus 2 j omega. From this one, 12 omega 4 minus 9 omega 2 plus 1 over j into 6 omega 3 plus 2 omega. You can see the denominator is a imaginary part. Then real part of the ZLC j omega is equal to 0. Then it is a non-negative and real. Then fifth property also satisfied. And the last one, the sixth one, says must have positive and real residues for all pole on the j omega axis. For that one, we have to do the partial fraction expansion. Set del C is equal to 12 S4 plus 9 S squared plus 1 over 6 S cube plus 2S. For this function, the degree of the numerator is greater than the degree of the denominator. Then we can write the partial fraction expansion as plus 1 over 2S. Sorry, B over 2S. CS plus D over 3 square plus 1. Now we have to find the values of A, B, C and D. For that one, I multiply both sides by this. Then I can obtain 12S4 plus 9S squared plus 1 is equal to AS times 6S cube plus 2S plus B into 3S squared plus 1 plus 2S into CS plus D. To find the value of A, B, C and D, first I consider the s to the power 4 factor. Then this side is left hand side and this side is right hand side. From the left hand side, the value of s to the power 4 is 4. Sorry, it is equal to 2, 12. Value of the s to the power 4 is equal to 12. 12 is equal to From the right hand side, it is equal to 6 times A. 6A. From that one, A is equal to 2. And I consider this S cube. There are no any S cube term in right hand side, and there are no any S cube in right hand side. And then I consider S to the power 2. From the left hand side, 9 is equal to 2A. From this AS into 2S, 2A plus 3B plus 2C. 2C. 9 is equal to, value of A is 2. 2 into 2 plus 3B plus 2C. 3B plus 2C is equal to 5. Then I consider this to the power 1. From this side, value is 0. It's equal to, from this side, it is equal to D. Value of D is equal to 0. Then S to the power 0. 1 is equal, from this one, left hand side, value is 1. And from right hand side, value is B. The value of B is 1. From this one, 3 into 1 plus 2C is equal to 5. 2C is equal to 2. C is equal to 1. These are the values for A, B, C, and D. Then I can write the final equation. Z del C is equal to 2S plus 1 over 2S plus S over 3S squared plus 1. This is the partial fraction expansion of the given impedance function. Then the sixth one says must have positive and real residues for all poles on the j omega axis. These are the poles. We can obtain pole from these two values. Then if we consider the residues, here 1 and here residue is 1, then all are real and non-negative. That means positive. Then final condition also satisfied. Then let's move to the additional properties of LC driving point function. The first one says the function must be a ratio of even, odd, or odd even polynomials. In this function, the maximum degree of the, in this function, the s to the power 4 and s to the power 2 are the numerator polynomials, and the denominator polynomial is s to the power 3 and s. You can see this numerator has even polynomial, and the denominator have odd polynomial. Then this condition also satisfied. And second one says poles and zeros lie on the imaginary axis and are simple. You can see in this explain pole lie in imaginary axis and pole of are simple. Then third one is highest power of the numerator and denominator should be differed by unity. If we consider highest power value, numerator polynomial is 4 and the denominator polynomial is 3. The difference is 1. And for the lowest power, numerator value is 0, and the denominator value is 1. The difference is 1. Then the third condition also satisfied. For the fourth one, there must be a pole or zero at the origin. You can see there is a pole in the origin. Then that one also satisfied. And the last one says poles and zeros are alternate. You can see start with the pole 0 for this side, pole 0. These are alternate. Then last condition also satisfied. Then we have to construct the final LC network. For that one, I rewrite the partial fraction expansion again. 2s plus s over 3s squared plus 1 plus 1 over 2s. This is Z1, Z2, and Z3. These are the small pieces of impedance value. If we consider the impedance of the inductor, we can write is equal to Ls. And if we consider the capacitor, the impedance value is 1 over Cs. Then if we consider Z1, it is equal to 2s. It is more equal to inductor value of 2, L1. If we consider this Z3, it is 1 over 2s. It is more like 2 capacitor value of 2 farad. Then we have to consider the Z2 component. It is equal to S over 3s squared plus 1. For that one, I consider the admittance value. Y2 is equal to 1 over Z2 is equal to 3s squared plus 1 over s. We can rearrange 3s plus 1 over s. If we consider the admittance values for inductor, YL should be 1 over LS, and for the capacitor, YC will be CS. If we consider these two parts, I consider as YA and this one YB. For YA, it is like to a capacitor with the value of 3 farad. And for this YB, it is more like to inductor with the value of 1, which is L2. You can see the combination of these two elements are shown in plus mark in admittance. For the admittance, plus mark means parallel connected. These two components are connected in parallel, C2 and L2. In the final circuit, we can get the impedance value. These are shown in plus mark. That means Z1, Z2 and Z3 component are connected in series. Then we can draw the final circuits. We can obtain the total impedance ZLC at these 2 points. This one L1 is equal to 2 Henry. C1 is equal to 2 farad. C2 is equal to 3 farad. L2 is equal to 1 farad. This is the final circuit. This one is Z1. These two components are Z2, 2, and this one is Z3. These are connected in series. That is the final answer of this example. I hope you all understand about this example. First, we have to check whether the function is realizable by examining these properties of the passive RLC function, and then you can consider the additional properties also. If all the conditions are satisfied, we can use the partial fraction expansion to expand the equation and break into small impedance part. Then we can find the value of each component, and we can combine all these components Z1, Z2, and Z3. That is the total process of first of all. Thank you.